miss.
Hello, and welcome to Team E1's Capstone project, Octo Plus. We have developed a custom plugin for the Octo print system, which allows for the automated detection of errors throughout a 3D print. Combining our custom computer vision algorithms with the Octo print environment, our system allows for hands-free automated monitoring of the entire printing process.
But as a recap, the goal of our project is to create an automatic error detection system for 3D printing using a combination of computer vision algorithms and an already existent maker software, Octoprint, which is currently used to let makers monitor their 3D printers. To briefly explain how our overall system should work, first, the user submits their G-code file into our modified version of Octoprint, Octo Plus. Our system takes that G-code and creates an array of 3D models of the print, where each photo in this array is the model at a different layer. Then, the print will begin and start the error detection loop. Every time the printer changes its Z location, our camera takes a photo and sends that into our edge detection algorithm, which will create an image showing only the edges of the print. This is compared to the model at the current Z state using Hausdorff distancing, and depending on that output, the print will be stopped or it will continue on as normal, and the checks will continue with every change in Z position until the print is complete. We can narrow down the main pieces of our technology into 4 different categories: the G-code modeling, the edge and error detection, the 3D printer working with Octoprint, and our plugin Octo Plus. First, let's talk about the G-code modeling. There are 3 main components that go into creating the models from the G-code. The first step is parsing through the G-code to get all of the plot points for the print. This is done by looking for the print command G1 followed by the XYZ coordinates and placing those into 3 separate coordinate arrays. Once we have all of the plot points, the program then combs through the Z coordinate array to get the index of the beginning of each new layer. And lastly, the program plots and saves a series of images of the print being built up. To plot each layer on the same graph, we had to hard code the axis values to be the max value from the whole print, so that none of the graphs would be distorted and so that they would not be changing axes from frame to frame. As well, to aid in the error detection process, the program masks out the grid lines and axis labels that Python automatically adds to every graph so that these images can go onto our edge detector and there will be less room for errors to occur.
Once we have the models for the piece we want to print, the printer will execute its G-code, and this is where our edge detection and error detection come into effect. In order to detect the printed object, we first have the user input the HSV or hue saturation value of the filament being used. This allows us to roughly mask out everything but the printed object in the image. For each layer of the print, our camera takes an image of the print at the current state, and then we apply the Canny edge detector on this masked image. This involves finding the horizontal and vertical intensity gradients. The edges are further made clear by suppressing the non-maximum intensity pixels in this processed image. By thresholding and keeping only the strongest edges, the edge image is ready for the comparison. The model of the current layer height is projected onto the image plane, where we could find the edges of this processed image as well. The Hausdorff distance allows us to compare these 2 edge images. This distance metric finds the minimum Euclidean distance from each point in set A to every other point in set B. The minimum Euclidean distance from each point in set B to every other point in set A is also computed and the final distance between the sets is the maximum of the two distances. This distance indicates if there are points in set A nearby some points in set B. Here, sets A and B are the two edge images. After we have a distance or error between the model and the image of the current print, we decide whether the print is erroneous. A visualization of the Hausdorff algorithm is shown from McGill University. The red and blue points correspond to two different sets. For each red dot, the distance to every blue dot is computed, and we choose the shortest distance. Then, the Hausdorff distance is the maximum of these two distances.
In addition to creating these algorithms, we had to find a way to integrate them as well. We did this by creating our own plugin to work alongside Octoprint.
The Octo Plus plugin is the main interface between our algorithms and the 3D printer. We have made simple additions to a bare-bones Octoprint plugin, allowing us to capture images on each z-index change. After a picture is taken, we then run our previously described image processing and error calculations. The plugin also allows for the user to choose the HSV value used to mask out the object in the image.
Alright, on to how the printer bot worked. Oh, wait. Yeah, so my computer exploded, and then the printer bot exploded. That was fun. Suddenly, we were plunged back into medieval times. Having dug up and revived an ancient MacBook Pro from 2010, we set about diagnosing the printer troubles. Apparently, the design of the Rev F4 version of the printer board, the board controlling our printer bot, included a defect. The MOSFET attached to the Z-probe input in these boards had a tendency to fail, and ours survived only up until the onset of the quarantine. The bad FET was replaced with a more reliable BJT, but the printer still failed to level itself. Apparently, the inductive Z-probe had also failed. Its indicator LED still correctly triggered upon proximity with the metal build plate, but upon further inspection and research, we determined it was no longer able to create a voltage drop large enough to flip the transistor. After waiting weeks for a replacement, we installed the new inductive probe and uploaded the modern Marlin 2.0 firmware to the printer, making sure to switch the logic of the probe. The original was a PNP, while the replacement used NPN. After that, the printer bot was finally back to printing. Considering the setbacks this project encountered over the course of the turbulent second half of the semester, there are plenty of tangible future goals ahead. Namely, generating 2D projections adjusted to match camera position and angle would greatly impact system reliability. Another key area to move towards would be to develop the system with a more generalized design, such that it could work with a wider variety of printer form factors. The vision algorithms could be augmented with the addition of color segmentation and point cloud generation. Adding a second camera to perform stereo vision would also be an excellent way to enhance the system's fidelity. Finally, more features aimed at better interfacing with users would be a huge plus. Among these are a proper graphic user interface to be added to the Octoprint interface, as well as a notification and warning system that could directly alert users when errors were detected. Further distance stretch goals would include the design of a motorized gimbal that could direct and focus the camera towards different points throughout a print, as well as implementing time-of-flight sensors to more accurately measure print features.